Hello. Now we will calculate the capacitance of this concentric spherical shells. So there are two concentric spherical shell. Inner shell is having a radius A and the outer shell is having the radius B. So there are two bodies basically. So if I want to calculate the capacitance, what I'll do, it's the same thing. We'll segregate the charges. Positive we can place only one surface. I'm calling this as 1 and this as 2. So let's put the positive charge onto the inner surface. So I'll be giving the positive Q charge onto the inner surface. So negative charge I'll be giving to the outer surface Q. And since the system is symmetric as well as spherical, we can say the charge which we are giving to the inner surface as well as outer surface, that will be distributed uniformly over to the surface. So positive charge will distribute uniformly over to the inner surface and the negative charge will distribute uniformly over to the outer surface. Okay. So this is the positive charge over to the inner surface and there is a negative charge over to the outer surface. And in this case, we want to calculate the capacitance. But before calculating the capacitance, let's check the electric field in different reasons. So there are three basic reasons. There is reason 1 which is inside the inner shell. Reason 2 is between inner shell and outer shell. This is reason 2. And there is a reason 3 outside the complete outer shell. So this is your reason 3. Okay. So let's go for quick study. So what I'll be doing, I'll be making 3 Gaussian surfaces. So these 3 Gaussian surfaces I'm making. These are the 3 Gaussian surfaces. This is G1, this is G2 and this is G3. I've made 3 Gaussian surfaces and I'm making the Gaussian surface to calculate the electric field. Because in this case, we don't have a ready-made potential formula, so I'll be calculating the electric field first. Okay. So for G1, Gaussian surface 1, if we apply the Gauss law, it will be integration of E dot ds is equals to q in upon epsilon naught. Since symmetry is there in all 3 Gaussian surfaces, that there is a symmetry. And due to the symmetry, we can safely assume if there will be electric field, that will be radial in nature, anywhere if there will be electric field. And the area, it will be parallel to the area vector, whether you talk about G3 or G2 or you talk about G1. So the angle is going to be 0 between E and ds for all 3 Gaussian surfaces. At the same time, over to individual Gaussian surfaces, the magnitude of electric field will be same. So if I talk about G3, everywhere onto the G3, electric field magnitude will be same. If I talk about G2, everywhere onto the G2, magnitude of electric field will be same. And the G1 also, the magnitude of electric field will be same. Okay, so let's first calculate for G1. So angle is 0. So this gets converted into EDS and that is equals to Q in upon epsilon naught. And if you look at G1, there is no charge inside the G1. That makes EDS to be 0 and that makes electric field to be 0. So electric field in G1 region is 0. There is no electric field inside the G1. So basically from center, if you see from center to surface 1, the potential will be same. So whatever is the potential at point 1, surface 1, it will be same till the center. Now we'll go for G2. If I apply the same thing, the thing is this formula will remain same. So ultimately you are going to get this formula. So if I apply for G2, it will be E integration of ds is equals to Q in upon epsilon naught. Q in upon epsilon naught. So this is the G2, this is the G2. And you see inside the G2, the charge is plus Q. So that becomes Q upon epsilon naught. That will be equals to E. The ds, that is the integration, that is the area basically. So if that area is, the radius is r, small r, in that case, it will be 4 pi r square. And if you take that value onto the right hand side, it will become 1 upon 4 pi epsilon naught Q upon r square. That will be the electric field, and where this r will be more than A but less than B. This is in G2 region. Okay. Now let's go for G3 region. We'll come till this point. So E integration of ds will be equals to Q in upon epsilon naught. This is the G3 region. So inside this G3 region, if you see, there are two charges. The outer surface is having a minus q charge and inner surface is having total plus q charge. If you add both of these charges, it becomes 0. And that leads to E is equals to 0 for G3 region. And for that, this is the value from R more than B but less than infinity, till infinity. And this is the value from this E is 0 for R more than 0, less than A. Okay. So you see, for G1 and G3, electric field is 0. There is an electric field only in between these two spherical shells. Electric field is only there between these two spherical shells. So you see, in this region, since electric field is 0, so in this region the potential will be same. The same potential will be there at infinity and the same potential will be there at the surface. So what I can do here, generally we assume the potential at the infinity to be 0. Since we assume the potential at infinity to be 0 and the potential at infinity will be similar to the potential at this surface, which is the 2 surface. So I can assume that potential at second surface to be 0 because the potential at second surface is similar to the potential at infinity. It will be same as infinity. Okay. Now let's calculate the potential at one surface, surface 1. So if I want to calculate the potential at surface 1, there will be two types of potential at surface 1. One due to the spherical surface, inner spherical shell, and second due to the outer spherical shell. So first I'll put the field potential due to the inner shell. Inner shell will be equals to 1 upon 4 pi epsilon naught total charge, which is plus q upon small a. That's the potential due to the inner spherical shell. Now we'll calculate the outer spherical shell. You see, this outer spherical shell, if you want to individually calculate the potential due to this outer spherical shell, then if you remember, whenever we talk about the spherical shell, inside the spherical shell, due to the spherical shell, potential remain constant. So I want to calculate the potential for all inside point due to this spherical shell. So that will remain same. Whatever is the potential due to the outer shell at the surface of the shell, that will be same as the potential at surface 1. Okay. So the potential of surface 2, this surface at its own surface, is 1 upon 4 pi epsilon naught q upon b. Because see, because of the outer shell, if you want to calculate the potential at this, that will be total. For that, you have to place this charge at the center and then you calculate. So that becomes 1 upon 4 pi epsilon naught q times of 1 upon a minus 1 upon b. That is V1. So V will be equals to V max minus V minimum, and obviously V minimum is 0, V max is this value. So by putting this value and simplifying this value, I'll be simplifying it, it will become Q B minus A upon AB. That is the V potential. Now from here we can calculate Q by V. By rearranging Q by B, we will get 4 pi epsilon naught A multiplied with B divided by B minus A. That's the value of Q by B we are getting corresponding to this structure. Now this equation we will compare with standard equation. And the standard equation is Q by V is equals to C. If I compare these two equations, the value of C, we get 4 pi epsilon naught A into B divided by B minus A. Okay. This is the capacitance due to this structure. Okay. So this formula one can memorize, and in this case, if you see, in this case, if the radius B tends towards infinity, because see, if, just to check, if B becomes infinity, if B becomes infinity, the outer shell goes to infinity, then this is not a two shell case, this is a one shell case, which we did earlier. So if B tends towards infinity, this value we can further modify. Then this value will be equals to 4 pi epsilon naught And the thing is, I'll divide denominator as well as the numerator with b. I'll divide it. So if I divide the numerator with b, the b will cancel out, and here it will be 1 minus a upon b. Since b is tending towards infinity, then a upon b will be 0. Then this c will become 4 pi epsilon naught a. This is the same formula we derived earlier. Okay, so if this two concentric shell case converts into the one shell, the same formula we can get from this. So this formula one can memorize. Okay, this is a derivation. In that case, we learn when we are using the two concentric spherical shell. In that case, the electric field is only confined within these concentric spherical shell. So wherever the electric field is, there the energy is. So in this case, the energy is confined within the region. So if the energy is confined within the region, it will be better for us to utilize this energy for some purposes. So this case is better than the case where when we were using the single spherical shell. Okay, so when we are using the double body system, and in case of double body system, the electric field can be confined within the bodies. That will be a more useful case. That's why when we make the capacitor for general use, we use two surfaces, we use two bodies, so that the electric field can be confined between those two bodies, and the utilization of that electric field, electric energy should be more. Okay, so this is a derivation, and this result one should memorize. And we also learn how to get this formula from modifying this one. Okay, so I hope you understood this. Thank you.